Yeah, thank you very much, Maxine. Thank you all for being here. It's also very exciting for me. It's, believe it or not, it's the first day that I've been to the ESI. Also, I've been now in Julian for more than 3 years. Yeah, so I want to talk about how we couple more than one atom that is individually controlled to an optical resonator. So this is the picture that we took in lab. You can see already the shades here on the right and left. This is like the scattering light from imaging a tweezer array that's inside the cavity. So you can see here the image of several atoms in optical tweezers. Now, if we think about this, then why would you want to trap them in tweezers? Why do we actually want to do these kind of experiments? Well, if we think about the development of the last couple of years, then most of you, when it comes to tweezers, you think about these kind of platforms, these kind of experiments where you have now individually controlled traps, so you can arrange them pretty much how you want. So there's this kind of preparation step that's very, very useful. Yeah? So we can really be certain that we have exactly one atom in each of those traps, and we can move them where we want to have them. Then we can couple them with a very strong coupling force on the order of several megahertz with a Rydberg coupling, even over optically resolved distances. Very, very nice. And there's also this kind of useful part that we can reconfigure them, so we can move them around and therefore generate new geometries or maybe also more complex circuits of the protocol. Now, what is this based on is the Rydberg interaction. Yeah, so that means if I bring my second atom close enough, then the second atom experiences energy shift due to the Rydberg interaction between two particles. And I want to make this analogy that here, what we are trying to do is an alternative way of having two atoms interact. So instead of having a Rydberg interaction, yeah, so a dipole-dipole interaction here, instead of that, we have an interaction that's mediated through a light field. So if I have a light field that's strongly coupled to my two-level system, we get this doublet here in the interaction splitting. And that means if I bring a second atom and I couple them simultaneously to a cavity, there's this very, very strong light-atom interaction that mediates the light between these two different atoms. So what I can generate with this is this very, very strong interaction that is different from the Rydberg interaction in the sense that it's independent of the distance. As long as these two atoms are both seeing the same cavity field, I still have that very strong interaction. That's a very, very nice knob to have, that we can now go also for longer distances with these interactions without actually having to move those traps around. Now, these can be extremely strong, so you can reach hundreds of megahertz with these coupling strength if you go to very, very small mode volumes. So in that sense, it's a very, very strong coupling. And we have also an effective interaction that actually, as I mentioned, like it goes over any kind of distance. So it goes through the cavity field, and therefore I can build my setup as large as I want, as long as it covers only the single radiation mode. I have an additional knob by not only coupling them all identically to the same cavity, but by with microscopic control, I can now generate a situation where not all atoms couple in the very same way, but they have slightly different coupling strengths. So I can control these individual coupling strengths of the atoms in the cavity if I have high resolution access in the system. So I can do this, for example, through local light shift and program those interactions. And I want to highlight that there are two big advantages that actually take quite some time when we think about larger and larger tweezer arrays. One is that we don't have any preparation or sorting that we need here. We need to know where the atoms are. Each tweezer will initially contain 1 or 0 atoms, but we don't need to move them around because all of them are already coupling to the cavity mode. We just need to know where they are. We don't need to move them. And we also don't need to do any kind of reconfiguration if we go away from a certain coupling setup. Yeah, is the question? Yes, the interactions are atom to the cavity and mediated through the cavity. They are also between the different atoms. Yes, to the coupling strength of those atoms to the same cavity field. So essentially, the coupling strength of each atom to this common mode can be dialed in. Yeah? And with this, you get these kind of programmability. Yeah? So we replace our Rydberg blockade now by the photon blockade mechanism. We have a tunable coupling strength of each atom, which we can either do by applying local light shifts, or I could, in principle, also just move them a tiny little bit out of the cavity mode. That would be a different way how to do that. Both are viable solutions here. And that allows me, in principle, to have complete control over the interaction graph of these atoms to the common cavity mode. Now I can do, excuse me, yeah? Yes. Yes, that's correct. Yeah. Okay, so if you want to have like, so you essentially have n knobs, right? N knobs for n atoms, but they are n squared coupling terms. Yeah. And if you want to go beyond n knobs, you have to go to either sequences where you dynamically change them, or you have to go to multiple laser beams that mediate different kinds of couplings. But by itself, you just have n. You have to do a little bit more if you want to go beyond n knobs. Yeah. Lucy? Yes, you could do this either through a Raman mechanism or you do it directly on resonance. They're both options are possible. We are not doing this yet. This is just like an idea. As you've seen, we have atoms coupled to the cavity, but they are inside this cavity. But we are not yet at the point where we're doing Raman schemes or other kind of. So there are different ways now that I can do interesting physics with this kind of setup. So, for example, I could generate long-range entanglement by like coupling all of these atoms simultaneously the same way to the same cavity mode. I can generate this kind of symmetric entangled state. I can then go away from this and generate a bit more complex states by, again, tuning my knobs, my coupling strength individually a little bit. And then you have these kind of photon couplings that would then couple like distant atoms. Or I can also have like new state preparation schemes where I use these global couplings for more efficient ways to generate certain target states, kind of bypassing finite size limit gaps that would shrink otherwise, but with the long-range couplings, they can remain a bit larger to have a faster preparation scheme. One example is, for example, geodesy states. So there's a constant gate sequence that you can choose, or constant length of your preparation sequence, and the fidelity in principle, at least from the conceptually, is not dependent on that. So that's quite useful if you have global pulses that you can actually also generate long-range entanglement in a quite efficient way. I could, instead of that, also now go away from these symmetric couplings, and for example, I can have a situation where I have like different kinds of random couplings over time. And then if I would have factorizable coupling, so it's exactly these n knobs, right? I already get a faster scrambling, and then if I want to have even faster scrambling, I would have to like dynamically change them as well. So these are the kind of experiments that I can do here. And the prerequisite for this, for all of these kind of schemes, would be to have these long-range couplings in the system. Now, I can also, instead of doing this in a kind of coherent fashion, I could also use measurements directly to do certain protocols in here. I could, for example, have non-destructive readout in my system. I can look at dissipative preparation of my quantum many-body states in terms of like dark states, and I can also use the cavity as a measure to measure stabilizers or to do quantum error correction. So just as an example, so I can, for example, in this case, it's a two-level system, two atomic two-level systems, where I can find ways to now couple the different states in a way that my dark state is a Bell state, and therefore I can drive my system into the Bell state that is stabilized by decay in an efficient manner. Here also I can read out my state. This is an experiment that was done in the Esslinger group long ago, and what they did, they sent single atoms through the cavity, and you can, in a very quick readout time of faster than microseconds, and with these kind of suitable cavity parameters, you can measure your individual atomic state. So that's much faster than, for example, fluorescence imaging usually, which helps you, of course, in the speed of the sequence. So you could, for example, envision something where you load your atoms, you initialize the state, and then you would evolve your state, and after the readout, you can continue with the initialization. Since this is a non-destructive measurement, you can kind of continuously use your same atoms there. They're just where they are, and the state is, or the system remains where it is. So this goes really fast, and is a good path towards really fast cycle times on the order of 100 Hertz or faster even. And what it means, or what it involves, is that we would have like one atom that is particularly strongly coupled to the cavity at one point in time, and then we kind of change this in time, and then through the time trace of the outgoing photons, you can detect which atom was in state 0 and which atom was in state 1. You could also use this for state preparation. For example, in this case here, from the blood group, and they were using this to generate entanglement in ions by dissipative measurements. So this is also another way that we could use in cavities and extend this to more than a few atoms by measurements of the state, and depending on the readout, give certain feedbacks on the atoms, the atomic state. This is another example where there was a collective measurement done. This is from the group of Jakob Reiche in Paris, where the global coupling to the atoms is complemented by a measurement channel, and then in a kind of quantum xenodynamics way, you generate this Dicke state from an initially unentangled state, or this W state. So there's a non-destructive collective measurement that drives you towards an entangled many-body state. So this would be another route to do, but also I want to emphasize that we actually have here a system that has a photon interface. So the atoms are naturally coupled directly to the cavity, so we can also use the quantum optics part of the setup by doing actually now many-body quantum optics with individually controlled atoms now, or go towards quantum networks where we use the outgoing photons as information carriers from one cavity to a duplicate of the setup. And if you look at this in the past, at these kind of setups, they typically look like this. So we have either ensembles in cavities where we have like an all-to-all coupling without individual atom control. We've also had some programmable couplings in these kind of ensembles by creating several sub-ensembles and coupling those again to the light fields. There are also examples of single atom, of a few atom arrays with like an all-to-all coupling in this cavity. And then also when it comes to programmability, this was also done already on the two-body level, particularly. A few body level, even like I think up to 5 or 6 in the group of Gerhard Rempe. So there's kind of different ways or different flavors of the experiments that have been done recently with atoms in optical cavities, and when it comes towards the controllability. And one important measure for the coherence in the system is the cooperativity, which tells us how strongly I coherently couple my system over the incoherent losses. And what we can kind of summarize this in a way that the most single atom quantum optics likes to sit up here, where I have a very, very strong cooperativity and a single atom that is controlled inside this optical resonator. And on the other hand, what we have also is a collective quantum optics, where we have an atomic ensemble that is coupled to the optical cavity. And here I'm not required to have a high single atom cooperativity, because collectively I can reach the strong cooperative regime again, even without having the single atom being strongly coupled to the cavity. So essentially what we want to access is this regime up here. Down here would be, I suppose, not quantum, single atom optics or something. Here would be the quantum optics, but on a many-body level with control. So not in a collective fashion, but actually with a single atom control. Now, why is it so difficult to get there? Well, there's some kind of fundamental considerations that make it quite hard to reach this regime. So, and essentially this boils down to the battle of control versus coherence. Yeah? So if I want to have very high control, usually what I want is between my cavity mirrors, I want to have a very high optical axis, so a large numerical aperture that allows me to access this. So what I want is some small mirrors and maybe large space here for a microscope objective. And that is usually what you would need to have a very high level of control. On the other hand, if I want to have coherence, I want to have a high cooperativity. And in the end, the cooperativity, although it looks like a quantum quantity, in the end, it's a geometric quantity that is associated to the angle. So this angle theta here of my mode, that determines the cooperativity in the system. And if I want to have a high cooperativity, well, this angle here will go up. So I need to find a way how this larger angle here does not coincide with this angle here. So the coherent versus the incoherent losses, so you can measure the this number that was like. It's just this number, yeah. There's not an independent. You can measure these numbers, okay, but there's nothing else. Yeah, it's simply that number. So the coherent, direction is d squared over kappa gamma, the atomic and the cavity losses. But there's another way to express this, which is the mode. So essentially, what it means is that it's proportional to the mode diameter. So you want to have a small mode diameter, inverse proportional. The smaller mode diameter gives you a higher cooperativity, and the mode diameter tells you the divergence of your mode. That is why I was relating this to this angle, and this is why experimentally it's not so easy to access this regime, because there are kind of these two things here that collide a little bit. Yeah, so you want to have this angle large, but on the other hand, you want to have it small such that the mirrors can be small, and you have a large optical axis here. Yeah, so it tells you how coherent your system is, right? Yeah, okay. So it tells you. It is a measurement. Yes. It is a measurement. It's a measurement for how coherent your interactions with the atoms are. Well, in the end, yes, exactly. The fidelity of that, yeah, exactly, yeah. So that's why we were striving so much to get this coherence, this cooperativity up here. So there's kind of this compromise that you have to do here, and usually what people then do is they choose mirrors that are in some way either adapted to one or the other. Yeah. So if you want to, for example, have just a single atom inside here, you may be able to get this in here without having a very large angle theta here. So you bring your mirrors very close to another. On another, you let your atom travel in there in a way that doesn't rely on like having a tweezer array, but maybe with a lattice or something. And then you can actually bring your single atoms in here. Or as we've seen earlier with the Esslinger experiment, they let the atoms actually drop through. Yeah. So this is not a solution that we want to have here. So we have to find a way that kind of combines these two in a suitable way. And what we've chosen to do was to use fiber tips as cavities. This is a technique that's been pioneered by the group of Jakob Reiche in Paris, and also other groups have worked on this. So what you do is you shape the front end of a fiber tip or of an optical fiber in a way, so in an ablation process. So you shoot a CO2 laser there that is absorbed by glass, and then the shape of that incoming beam is directly giving you the ablated profile in the front. So that means in the center, what you get is approximately a parabolic mirror, and that means that you have a mirror surface here, which can have a very, very small mirror diameter. Yeah? So your fiber is 125 micron in diameter, and at the same time, you have very high radius of curvature, higher than something that you would be able to do mechanically. So with such a setup, it's quite useful. Yeah. So we have a very high optical access because these mirrors are very, very small in diameter. We can achieve very high coupling because the radius of curvature is very small, and therefore we get extremely small mode volumes in the system. And what's also useful is that we directly have an interface to an optical fiber. So we have if you want to go towards photon networks, we directly have an interface to fibers. Yeah, exactly. That's of course that's a compromise that you also face. Yeah, the smaller your volume, eventually fewer tweezers will fit in you. So we're working here right now. I will show you later on the order of 10, 20, 30 atoms, and we think we can go farther than that in the future. Yeah. So here's another thing that's quite dedicated is that now the mode diameter is just a few micron large, so it's quite involved to experimentally build such a system. So it took us several iterations, but now we have a happy setup here, which this is what it looks like. So this is inside a vacuum chamber. This is a Mako ring that is very, very stable. There's a piezo that allows us to stabilize the cavity length interferometrically, and then this length of the cavity here in this case is about 80 microns, so that fits about 30 tweezers. If they are like on the order of 2 micron apart or 3 micron apart. Yeah, so this is now the setup. It's we're using rubidium 87, and so the hyperfine transition here can be used as a qubit state of 0 and 1, and then we can couple this cavity to the excited state either resonantly or far off resonantly in the Raman process. These are the parameters of this cavity here, and so this gives us a quite high cooperativity, larger than 100, with these kind of parameters. So that because the mode volume is very, very small, yeah, and there's reasonably high finesse, that gives us this very, very coherent interaction in the system. This is what the setup looks like. We have a 2D mod here, we have a 3D mod chamber here, and then breadboard. So this is what it was looking like before we had the optics around, and this is what it looked like after we had the optics around. There's the fiber cavity sitting in here, and there's the optical fibers that go out of this. We can also move the setup out of the actual experimental optics around the setup, so it's quite easy to actually exchange the cavity for example, upgraded versions in the future, and also in the past so far already. Yeah. So the way we use we now transport the atoms into this cavity and generate the tweezers there. This is what it looks like. So we start with a mod above the actual cavity. That's required because the length of the cavity is too short to actually do laser cooling inside. Then we have this is what the apparatus looks like. It's quite, for the experimentalists, it's actually quite interesting because it's a mod with very, very strongly tilted beams, which allows us to have actually optical axis along the microscope axis, but also a mod along the axis. And then we can now load these atoms into a dipole trap that we then transport down with an AOD. So we have an AOD that generates a single beam, and this is then transported from the mod into the cavity with this dipole trap. So this is what it looks like here. This is we load the atoms from the mod, and then we move them down into the optical cavity. And here you can see the cavity. And then once we are down there, we have we switch on the tweezer array, which is created by a second AOD that now generates this column of frequencies and this columns of microtaps that we then send through an optical microscope objective with an NA of about 0.5 onto the atoms into these individual tweezers that are a few micron apart. And then this allows us now to trap these atoms here inside this optical cavity. Here's on the order of 10 atoms. We also have increased this now to 20, 25 atoms. And again, you're right, the length right now is the limiting factor for the number of atoms, but one can envision cavities that have similar coupling and are slightly longer even. So this is the imaging. The imaging is a little bit more subtle than usual because you have surfaces nearby, so there may be actually some kind of stray light that is a bit stronger than if you would just have something right in vacuum. So we were a bit worried about this, but we were still nevertheless able to get quite nice fidelities in the optical imaging. And then maybe as a quick outlook, we were able to see some coupling of the atoms to the cavity already. So this would be the cavity without an atom, and then if we would introduce some atom here, we can actually already see some coupling of the known mode splitting. So this is the state where we are right now, and we are working towards now generating 2 and more particle entanglement in this kind of system in a coherent fashion, also maybe in a dissipative protocol. And we are currently also setting up our single qubit control where we can generate Raman pulses that would drive the ground or the 0 and the 1 state. And then also we are also setting up right now the local addressing setup with which we can now dial in the coupling strength of each atom separately. So as a future outlook, what we really are aiming for is something that we can scale up from these 10, 20 atoms towards more than 100 atoms, and cooperativity larger than 100 should also be feasible with this kind of approach. Similarly, the readout fidelity of the cavity right now is not quite optimized yet. So the overlap of the cavity mode with the mode of the fiber is not perfect yet. So we think we can improve on that and therefore get even better readout of the cavity. For that, we built such a setup where we can build our own fiber tips. So far these were commercially bought, and so this is what it looks like. So this is a test plate here, and so you shoot short pulses with a CO2 laser, and then we can interferometrically measure the surface with sub-nanometer precision. It's really precise how you can actually measure the surface, and with that we are now aiming to generate cavities that have slightly higher finesse and slightly smaller radius of curvature, such that they can be a little bit longer but keep comparable cooperativities. Yeah, with that I want to conclude. I hope I convinced you that programmable interactions and cavity-mediated interactions are a great tool towards generating new kind of entangled states with atoms and tweezers. This is the team that I've been working with, particularly Franz, Stefan, and Johannes. I want to highlight them. They're working very hard on the cavity team, 3 PhD students. And also, if you are interested in visiting our labs, feel free to just pass by. And we are in Atom Institute. It's not quite that pretty of the building. It's another building, but you're still welcome to pass by anytime this week. And if you don't have time this week, but another time, then we are actually going to move very soon to ISTA, which is right outside of Vienna. You're also welcome to pass by there anytime and visit us and the labs. So we're going to move the labs by the end of the summer, and then the setup will also transfer there. There's another setup that we are currently building where we want to go for more programmable geometries also for Hubble-type systems. So we're building a setup where we have lithium in an optical lattice, and we want to go away from periodic potentials towards aperiodic potentials and new lattice geometries. So if you want to know more about this, let me know. I'm happy to talk to you about this. Yeah, and with that, I want to thank all of you. Thank you.